Hello students, so continuing our lectures on solid state physics, we will start with number of lattice points in a BCC. So in a BCC, as you know, there are 8 corners, and each contribution of each of those 8 corners is 1 by 8. So 8 into 1 by 8 plus there is a one atom at the center, or lattice point at the center, so that makes it 2 lattice points, or 2 atoms. The diagonal of an BCC is a into root 3, where a is the QH length and it is equal to 4r. So the packing fraction is twice, that is number of lattice points into the volume and divided by the QH volume. So that makes the value as equal to root 3 pi by 8, and which is 0.68. Similarly, in the case of an FCC, you have 8 corner atoms plus 6 face atoms, making total 4 atoms, and the diagonal is also equal to 4r is equal to a root 2. So putting these values into this packing fraction formula, we get the end result as pi by 3 root 2, which is 0.74. In the case of diamond, it's basically an FCC about so that makes it 4 atoms, and apart from that we have 1 at the corner atom and 4 at the faces, so total 8 atoms. And although its diagonal is same as is in the case of an BCC, however the nearest neighbors are given as 2r is equal to a root 3 by 4, so that makes the packing fraction 0.34. As you can see, 0.34. In the case of simple cubic, however, number of atoms is 1, and the radius and the QH length are related by this relation, showing the packing fraction as 54% or 0.54. Now, the number of neighboring lattice sites to a lattice site in a BCC is 8, and in FCC is 12. These are also known as coordination numbers. And a plane between two adjacent distance between two adjacent big plane is given as DHKL, and it is equal to 2 pi by g, which is this is the reciprocal lattice. In the case of diamond, a crystal with FCC, and which has 2 atom spaces located at 0, 0, 0 and 0.25, 0.25 and 0.25. And so if somebody tells you to find out the maximum wavelength possible, so what you will do for maximum wavelength, you need to put this sign theory is equal to 1, so that will make this value of lambda is equal to max. So putting the sign theory is equal to 1, and it is given that the value of the interplanar spacing is 3.6, so that makes it lambda is equal to 2 into 3.6, that is 7.2 Armstrongs. Now the energy of X-rays in electron volt, we need to find out. We know that the wavelength is 7.2 Armstrong, so putting the value using this formula is equal to h by lambda, putting all the values, what we get 1.7 electron volt. Now if we have been given some HKL indices like 212, 111, 200 and 311, and if you are asked to find out which one of them will not follow an FCC, will not present FCC, so automatically you can see that for an HKL plane to be in the FCC or to satisfy FCC, either all the HKL values should be equal to or should be even or odd. So in this case, as you can see, there is a combination of even and odd, 2 being even, 1 being odd, so this is not, this will vanish, it will not be present in the FCC. So peak. In the case of BCC, however, if the angle or the point of diffraction takes place at angle 30 degrees, and the wavelength of the X-ray used is 2.1 Armstrong, and you have been told to find out the primitive unit cell volume, then what you can do is the first acceptable HKL value for a BCC will be 110, because for a BCC H plus K plus L or H plus K plus L, it should be equal to even. It's the only possible way that can happen. The first case first is 110, and for a cubic, the interplanetary spacing related to the lattice cube visiting values formula. When we put the values of H, K and M, we get A is equal to T, and we know that D is equal to 2.1 Armstrong. Putting this value, we get to T by using sine theta is equal to theta is equal to 30 degrees, so that makes T is equal to 2.1. So putting that value, we get the volume of the primitive cell as 26.2 Armstrong. And in a diamond structure, the unit cell age length is 0.52, and we are close to find out the neutronic separation. So this is the formula that will be used. It's 2R is equal to 803 by 47 neutronic separation. It turns out to be 0.034 nanometers.